Hello everyone, greetings of the day. Dr. Nishant Sharan, designated as an assistant professor in Madanapalle Institute of Technology and Science. So earlier when we have met, I was discussing with the few fundamentals topic of electrostats, which was basically about the concept of charge, electric field, some problems on electric field. So today, once again, I'm here to discuss an important topic in the field of electrostats, Gauss law in electrostats. Yes, all of you are getting it very right. That definitely one of the topic which involves the complexity in application. While discussion in the class, sometimes I come across the query, sir, how to apply the Gauss law because the geometry becomes complex while we go for applying. Or in other words, you can say that students come across the problem of visualizing the geometry. So to I'm trying my level best in this lecture to make you understand the concept of Gauss law in electrostats and how to apply it for the variety of the problems, including the integral form, differential form, its application. Hope it helps you and erases all your complexities while you apply the Gauss law in electrostats. So let us have a quick far session on the Gauss law in electrostats. So as you can see, the earlier already I have discussed the electric charge, concept of the field. So we have already covered the electric charge, concept of the field. Then today we are here to go with the Gauss law in electrostats. So understanding the Gauss law in electrostat. To understand the Gauss law or to keep in mind the concept of Gauss law, first is that why it is needed. What is the need? So first is that its need is very simple because it is one of the very fundamental principle. There is a fundamental theorem which relates the electric field around a closed surface. That's very important. So here you also can say that is it the limitation of Gauss law? Yes, we would be talking more on it after going through the basics, applications, the first covering the required thing. Then definitely we will talk on this, that what about the limitations, or is it applicable to all the surface, yes or no. So that will be answered very soon. So Gauss law relates the electric field around a closed surface to the electric charge. So here are the two very important fundamental quantity. One is the electric field and another is the electric charge. And how it relates, that also we'll see. Then it is a fundamental principle in electrostats. And how can you think of that? Electric field might be important in everyday life. So as you can see, this figure, and let me illustrate this figure. As you can see, so we are having a positive charge at the center of a sphere. And we know that the electric lines of force goes away from a positive charge. Electric lines of the force goes away from a positive charge. That is what we know, right? Then here, to understand this one, we are having a term called as flux, as you can see the symbol. So first thing is that one should understand the term flux. So what is a flux? So flux is basically nothing. Nothing means it is simply that number of electric lines of force crossing through a given surface area. Once again, I repeat, number. Yes, you heard it perfectly right, clearly right. It is nothing but a number. And number of what? Number of lines of force. Yes, electric lines of force which are crossing through a given surface area. That's the called as flux. And the symbol used for this is phi. So phi E is nothing but the flux of electric field, the symbol used, and what it is nothing but the number of lines of electric field which is crossing through a given unit surface area. So one can write the phi E as E into area. But here again there can be a complexity or a question. To be very precise, suppose you are having this surface. This is a small elementary surface. That's fine. And electric field, and there is a vector, normal surface area vector. So this is a surface, so it's surface area vector. And the electric field and the surface area vector are making an angle theta. Here, as you can see, they both are in the same direction. There can be a possibility that direction of electric field is like this. There could be a possibility that this is my direction of electric field. And they are making an angle theta, right? So in that case, what would be the flux? Yes. So you have to take the normal component of electric field. And what would be the normal component of electric field? That's the very easy one can find. It could be using the geometry E cos theta. So E cos theta into A. So now what becomes the precise definition of flux? This is simply, you know that mod of A into mod of B into cosine of theta is nothing but a perfectly definition of dot product of two vectors, rightly said. Dot product of two vectors. So now here I am having, this is the mod of E, means magnitude of E. This is definitely the mod of A, and we are having the cos theta. So what becomes the definition of flux? So definition of flux is nothing but, so that definition, so formula becomes phi E is equal to E dot A. Yes. So this is the definitely nothing but a scalar quantity. A scalar quantity. This is basically a scalar quantity. Right. Fine. Now what does the Gauss law says? So a statement of the Gauss law, a statement of the Gauss law is very simple. It's just a one-line statement. Anybody can keep in his or her memory. It is saying that the net flux emanating from a closed surface. As in my previous slide also this thing was mentioned that closed surface should be closed. So emanating from a closed surface is equal to net charge within the surface. So mathematically one can write, definitely, mathematically one can write simply phi dot E, means flux of the electric field, is equal to, when you are writing that flux is equal to net charge enclosed by the surface. So phi dot E is equal to nothing but Q enclosed. This is the very simplest form of the Gauss law in electrostatics. So if I write like this, what I mean to say by this? So if you see that what I mean to say, or how one can really look for its proof, then so first thing is that one can write is that if I talk about the flux, so you know that flux is E dot ds or E dot A. Better here till now I will write the E dot A. So what is the electric field E due to a point charge? Yes, Q over 4 pi epsilon naught R square R cap. Yes, that is the definitely. And if I ask you that what is the elementary surface area in a spherical coordinate system? Yes, that also you know perfectly and rightly. R square sine theta d theta d phi r hat. So now if I take the, suppose the d phi e. So d phi e would be simply q over 4 pi r square q over 4 pi r square q over 4 pi r square epsilon naught. Sorry, missing here. So let me include that. R hat dot with the, yes, dot with the R square sine theta d theta d phi r hat. Okay, so this will give you the q by 4 pi not r square. You know that r hat dot r hat is 1, and if one is interested to find the total flux, so if one is interested to find the total flux, so that need to be integrated. So yes, that need to be integrated. So if you integrate this, that's the very simple, q by 4 pi epsilon not r square, and this integration we all know that is nothing but the surface area of a sphere. Yes, so surface area of a sphere is simply 4 pi r square. After integrating this, one would be getting this particular thing. Definitely, one would be getting this one. Yes, so this is nothing but the integral. It is nothing but the integral, right? Better I should write like this for your convenience, that yes, integral over the bound, right? This is what I mean to say. This is the integral over the bound. Yes. So here one can see that this 4 pi gets cancel out. So what I am getting is q over epsilon naught. So this is what is the basic thing. It says that the E dot ds is equal to q over epsilon naught. So moving ahead, so as you can see here, that this is what the electric field of a vector. So this is what, after doing that, let me complete that. We got the E dot ds is equal to q over epsilon naught. Or same one can write, if you take this epsilon this side, then surface integral epsilon naught dot E dot ds is q. And here again, we are having our new quantity. I will discuss that one also. That is the epsilon naught times E. So here is another new quantity, epsilon naught times E. So the overall here, let me summarize about the till now what we have discussed. So till now we have discussed is that Gauss law statement and mathematical form. That's very, very important. Mathematical form. So first mathematical form is that E dot ds, surface integral, definitely dot ds, is q in over epsilon naught. And another form one can write definitely is that epsilon naught times E dot ds is q in. And moment you write the epsilon naught times E, the physics says that this is having another name called as d. So one can write d dot ds. So what is this d? That also let us talk. D dot ds is q in. Yes. So d dot ds is q in. That's very important. So d is the flux density vector. Flux density. So new term, flux density. Yes. But so why I'm giving the stress like density? Because one should not remain confused that between the phi and d. Phi was the flux, d is the flux density. Phi is a scalar quantity. This is a scalar quantity. A scalar quantity. D is a vector quantity, as you can see. That's very interesting. And again, if one has to find the phi, he or she can write very easily d dot ds. So there's nothing but charge. Charge is nothing but the flux. So charge is also a scalar quantity. Flux is scalar quantity. So charge and flux are basically representing the same thing. So now this one is also called as the Gauss law in electrostats. That's very important. Gauss law in electrostats. So now what is the statement? The statement is that D dot ds is q in. So please keep this in mind, or E dot ds is q in over epsilon naught. So this is how we define the Gauss law in electrostats. So this is what I have already discussed. So now here in the engineering level especially, the two forms of the Gauss law are used. One is the integral form. So moment I write, see very carefully, D dot ds is equal to q in. This is called as integral form of the Gauss law. This is called as integral form of the Gauss law. Now what is the differential form? That's very easy. If I write, see, D dot ds is equal to q in. Suppose rho v is the volume charge density, then I can write q in as rho v dv, the volume integral. And if I apply the Gauss divergence theorem, then one can write, that is a well-known theorem, and definitely if both are equal, then del dot d is rho v. That's a very useful relation. Del dot d is rho v. So del dot d means divergence of the flux density vector is equal to the volume charge density at a given point. That is why this is also called as point form. So once again I repeat, the integral form and differential form are the very important. So one is saying is that del dot d is rho v. So divergence of the flux density vector is always equal to the volume charge density at a given point. That's very important. So let us do one problem that should help you. So I'm having one problem here. An electric field in a region of space near the origin that is given as E as a function of xyz is given as alpha xi plus beta times y plus y naught whole square j cap. So means, as you can see, the electric field is a function of x and y, and two components of the electric field exist. One is in the x direction, another is in the y direction. This exists. So the question is that if there is no charge at the origin, then the electric field is equal to this much. Just you can pause the video for a minute, and then you can try to solve it, and then you can verify your solution. So just think for a moment how one can show. So it is showing that electric field is alpha x I hat plus beta y times y naught square j hat, and one is required to prove. You have to prove what? That electric field is equal to this much. So how to prove? What should be your strategy? How one can move on? Just think of it, pause the video at least for a minute, have a pen and paper with you, try it out, then you can match your solution. Yes, so let us see. So just now we have seen that del dot d is rho v. So one can write, if it is the del dot d is rho v, one can write del dot e is rho v over epsilon. So that is what the first expression. Then taking the divergence. You know the formula for divergence in the Cartesian coordinate system? So yes, the formula for the divergence in the Cartesian coordinate system is like this. So partial derivative of the x component plus partial derivative of the y component. So when I take the partial derivative of the x component, it is alpha times x, where alpha is essentially a constant. So I will get the first term as alpha. When I will take the partial derivative of beta y plus y naught square, simply I will get the 2 times beta into y plus y naught, and y naught is a constant. So y plus y naught, so y derivative will be 1 and y naught derivative will be 0. So this multiplied with 1, which will give me the same quantity as this one, right? Now this is the okay. Now what is the question? question is saying that you have to show that if no charge is at the origin. So no charge means rho v, no charge, no charge. So no charge means rho v is 0. So moment I will get the rho v 0, I will equate this to 0. So I have equated this to 0, as you can see. So once we equate this to 0, y naught is minus of alpha by 2 beta, definitely. Then what I can write? I can write E as a function of x, y, z is alpha xi plus beta times y minus alpha by 2 beta square j hat. And as it is saying that at the origin. So at the origin, x will be 0, y will be 0, at the same time z will be the 0. So if you plug in here, x will be 0, y will be 0, and z will be 0. So there is no z component here. So only x is 0 and y is 0. So if I plug in here, x is 0 and y is 0, definitely I will get, you can check it out, one will get the, and if you will solve it, x will be 0, this whole term goes to 0. Y is 0, this one goes to 0. So you will be simply getting alpha square by, so here you will be simply getting alpha square by 4 times beta square, and one beta is here, beta square and beta, they will cancel out each other. So just plug in here 0, 0 and solve it, you will get your answer. So this is how the Gauss law works. This is one sample problem. So just one should see that how one can apply the Gauss law. To apply the Gauss law, one essentially needs a Gaussian surface. Now, what is this Gaussian surface? Yes, Gaussian surface is basically an imaginary surface which should satisfy certain properties. What are those properties? First property is that it should essentially be symmetric. That's very, very important. It should essentially be symmetry. So symmetry is the must. Yes. You can also say that then it comes to a limitation. Yes, 100%. So this is the basically also the limitation of Gauss law, because Gauss law is applicable only to the Gaussian surfaces, and the Gaussian surfaces should exhibit symmetry. So to a non-symmetrical surface, one cannot apply the Gauss law. So what could be the different Gaussian surface, how one can apply it, what could be its application, that we would be seeing in the next lecture. So thank you. I hope you have understood the Gauss law. As usual, you can ask any query, any comment, you can put it over, you can ask it. And once again, very soon, we will carry on with this thing. So you can put all your queries on the given link. Thank you. Thank you for today.